Alright, this is the second video on comparison tests, and we're going to be looking at two more examples. Before we get into our first example here, we're going to be looking at taking a limit as n goes to infinity with a natural log of n quantity raised to the 4.3 divided by n to the 0.3. We try to look at it, it's going to be of the form infinity over infinity, and so that means it's a candidate for L'Hopital's rule. So we're going to go ahead and take the derivative of the numerator, which will be 4.3 natural log of n to the 3.3 times 1 over n by the chain rule, and then over 0.3 n to the negative 0.7. That's going to be equal to the limit as n goes to infinity, 4.3 natural log of n to the 3.3. The 1 over n, the n is going to come to the denominator, and n to the negative 0.7 times n to the first will be n to the 0.3. So we'll have 0.3 n to the 0.3. If we try to see where this limit's going, it's going to be of the form infinity over infinity again. And so that is a candidate for the L'Hopital's rule. And so we're going to go ahead and apply L'Hopital's rule again here. All right. So this is the limit as n goes to infinity of 4.3 times 3.3 natural log of n to the 2.3 times 1 over n by the chain rule divided by 0.3 times 0.3 n to the negative 0.7. Now maybe you start noticing a pattern. The 1 over n, the n is going to come to the denominator, n to the negative 0.7 times n to the first, the n to the 0.3. So this becomes the limit as n goes to infinity of 4.3 times 3.3 natural log of n, that quantity, to the 2.3, all over 0.3 squared times n to the 0.3. If we examine this limit again, it's going to be of the form infinity over infinity. So we'll apply L'Hopital's rule again. This is going to be equal to the limit as n goes to infinity of 4.3 times 3.3 times 2.3 natural log of n, that quantity there, to the 1.3, and times 1 over n by the chain rule. I hope we're going to put that in there. Did we put it in there? Uh-oh. Well, let's put that 1 over n there. We almost forgot it. So there it is by the chain rule. So that 1 over n, the n's going to go to the denominator again. So we're going to look at the limit as n goes to infinity. 4.3 times 3.3 times 2.3. Natural log of n, that quantity, to the 1.3, all over 0.3 cubed n to the 0.3. Alright, so we'll look at the form again. Oh, it's infinity over infinity, so L'Hopital's rule again. So this is going to be a limit as n goes to infinity of 4.3 times 3.3 times 2.3. Bring down the exponent, 1.3. Natural log of n, that quantity, to the 0.3. Okay, times 1 over n by the chain rule. All over 0.3 cubed times 0.3 n to the negative 0.7. Okay, so we're going to have to continue this on the next slide here to finish this up. Okay, so the limit as n goes to infinity, 4.3 times 3.3 times 2.3 times 1.3, natural log of n, that quantity, to the 0.3 times 1 over n by the chain rule, divided by 0.3 cubed times 0.3 n to the negative 0.7. The 1 over n will come down again, and it'll make that n to the negative 0.7 become an n to the 0.3. This becomes the limit as n goes to infinity, 4.3 times 3.3 times 2.3 times 1.3. Natural log of n, that to the 0.3, all over 0.3 to the fourth power, times n to the 0.3. Again, if we kind of try to figure out where this is going, it's going to be the form infinity over infinity again. So apply L'Hopital's rule again. So this is the limit as n goes to infinity of 4.3 times 3.3 times 2.3 times 1.3 times 0.3 times the natural log of n raised to the negative 0.7, and then times 1 over n by the chain rule. all over 0.3 to the fourth power times 0.3 to the 0.3 times n to the negative 0.7. And is this thing ever going to end? Yeah, it's about done here. So the 1 over n, the n's going to come to the denominator, and I'll make that n in the denominator a n to the 0.3. So this becomes the limit as n goes to infinity of 4.3 times 3.3 times 2.3 times 1.3 times 0.3. Okay. 0.3 to the fourth times 0.3 will be 0.3 to the fifth power times n to the 0.3, and then the natural log of n to the negative 0.7. That's going to come down to the denominator. Okay. And now the numerator is a constant, but the denominator is exploding to infinity, so this limit is going to be 0. Okay, so we're going to run into this limit in the next problem. So we're doing the limit comparison test, and we have the sum n equals 1 to infinity of the natural log of n over n to the 4.3. Okay, and so, you know, you got to do some playing around in terms of what to compare it with. The 4.3, so you kind of have like a you kind of have a sort of like a p-series, of 4.3, but we're going to go a little bit smaller than that. We're going to do, we're going to compare it with the convergent p-series, p being 4. P is equal to 4, that's greater than 1, and so that means this is a convergent p-series. Okay, and so we're going to be looking to do the limit comparison test on this thing. So we're going to look at the limit as n goes to infinity of the natural log of n to the 4.3 divided by n to the 4.3 divided by 1 over n to the fourth. That's going to be the limit as n goes to infinity of the natural log of n to the 4.3, and then n to the fourth, because we take the reciprocal, we flip it over, or we take the reciprocal and change the operation to multiplication, that 1 over n to the fourth we're dividing by, all over n to the 4.3. And so if I had chosen p-series of 1 over n to the 4.3, the problem is the limit would end up going to infinity, and that doesn't tell us anything here. So if we're doing this comparison here, if we're going to try to show convergence, we want the limit to either be L or 0. That's either conditions 1 or 2 in the limit comparison test, either in your textbook or in the notes here or the previous video. All right, so this probably looks familiar. That's what we spent the last 2 slides going over. Well, almost. Let's simplify it. So the limit as n goes to infinity of the natural log of n quantity to the 4.3 all over n to the 0.3. And so that's what we did several instances of L'Hopital's rule. Eventually that limit was 0. And so this is the second possibility what we have with the limit comparison test, which says if the limit as n goes to infinity of a sub n over b sub n is equal to 0, and we know that the sum n equals 1 to infinity of b sub n converges, then so will the a sub n. The sum of n equals 1 to infinity of a sub n. So since the sum n equals 1 to infinity of 1 over n to the fourth is a convergent p-series, the sum n equals 1 to infinity of the natural log of n over n to the 4.3 converges by the limit comparison test. Okay. So it's possible you might be able to try another test, but this is coming from the limit comparison test section, so naturally that's something you're going to try. The only things we can really try is with the comparing with p-series or geometric series. This is not a geometric series, so you got to try something out with comparing it with some sort of p-series. You could also look at the partial sums. Maybe look at the sum n equals 1 to 5 or 10 or 15 and kind of get an idea. Does it look like it's converging? Does it look like it's settling down, or is it getting wild? Is it getting very large, very small? You can look at those things. All right, I have one more example. I don't know if it's in the notes, but we have one more example, and this is to illustrate the third criteria in the limit comparison test. Well, it's not a criteria, but it's the third kind of conclusion we have with the limit comparison test. And that says if the limit as n goes to infinity of a sub n divided by b sub n is equal to infinity, and we know that the sum n equals 1 to infinity of b sub n diverges, then the sum n equals 1 to infinity of a sub n diverges. So let's go ahead and take a look. So we're going to look at the sum n equals 1 to infinity of 1 over the natural log of n squared. Okay, we're doing a comparison test, and we can compare it to p-series and geometric series. That's pretty much what we compare it with. I'm going to attempt to compare it with the divergent p-series, the harmonic series. And p equals 1, that's the strength of 1, so that's our criteria for divergence in the p-series. So we have the sum n equals 1 to infinity of 1 over n. So we're going to look at the limit as n goes to infinity of 1 over the natural log of n, quantity squared, divided by 1 over n. So we're going to go ahead and flip over the divisor fraction, so we have n over the natural log of n to the second power. This is of the form infinity over infinity, so this is candidate for L'Hopital's rule. So it's going to be equal to the limit as n goes to infinity of 1 over 2 natural log of n times 1 over n by the chain rule. And that's going to be equal to the limit as n goes to infinity of n over 2 natural log of n. Again, this is of the form infinity over infinity, so we're going to go ahead and apply L'Hopital's rule again. And so it's going to be a limit as n goes to infinity of 1 over 2 times 1 over n. We'll rewrite that as the limit as n goes to infinity of n over 2. And that's going to be equal to infinity. And so the limit comparison test says in this situation that because the series we compared it with diverges, and we had the limit as n goes to infinity of a sub n over b sub n, where the series of b sub n diverged, so also the series of a sub n will diverge. And so that is our conclusion here. So since the sum n equals 1 to infinity of 1 over n is a divergent p-series, the sum n equals 1 to infinity of 1 over the natural log of n, quantity squared, diverges by the limit comparison test. Okay. All right. So you just got to get in there. You got to try them, work out the problems in the homework, rework the example problems in the textbook. Well, maybe not rework, but work out the example problems. Make sure you're understanding all the steps. Work out the video problems also. And just the experience will help out with what do I compare it with. And you're going to be comparing with p-series and geometric series. Alrighty. Well, stick tuned. What am I trying to say here? Stay tuned for the alternating series test coming up soon. So we'll see you next time.